So this is my Lab 6 falling object presentation by me, Neil Crowley. The experiment for this experiment, I recorded a video of a ball being thrown into the air and dropped back down. We then analyzed the motion of the ball rising and falling during each frame using a program called Tracker. It allowed us to track the ball rising and falling by each frame. This allowed us to analyze many different things that were affecting the ball, such as gravity and air resistance. Buoyancy is also a measurable factor in this, but the only fluid to be measured for the ball was the air around it, which we did with air resistance. We would find the average of the data by adding up the values and dividing it by the number of values, and we would find an RMSE value by square rooting the average value for each model. Our setup consisted of a solid color background of black to make the ball easier to track, a cam recorder to hold the recording device steady, and the ball to throw into the air and measure via video. Our assumption is that the best model for the ball dropping experiment will be the gravity and quadratic air resistance model. This is because this model accounts for more than the other two, so its margin of error will probably be less than theirs. This model accounts for a much more precise version of air resistance than the linear model, and the gravity only model doesn't even account for air resistance at all. The significance of the RMSE value shows us the size of error between the model and our data points. We generally want this to be as small as possible, and whichever of the three models has the smallest margin of error would prove to be the best model for determining speed and acceleration of the ball during its drop. These are our three graphs. This is gravity. It had a very straightforward consistency. So, I mean, yes, it's straight, but there's not too many things that it's only factoring gravity, so it's going to be straight and less precise. This one is linear air resistance, so it jumps around a little bit more, but it's still straight basically. But it accounts for more than just the gravity, so it's a little bit more precise than this one. And gravity and quadratic air resistance it jumps around more. It's showing more being affected by the ball, and it is much more precise than the other two. In summary, all the graphs accounted for gravity, but the most effective graphs are the ones that accounted for the most air resistance. When we consider something as simple as dropping a ball and measuring the speed and acceleration, we can get much more accurate results when considering as many factors as possible that are affecting the ball during the drop. And that ended up being our third graph, our third model. And this is a graph of all three. It jumps around a lot. And the conclusion was that the results of this experiment showed that gravity alone accounted for the least amount of things interfering with the ball dropping, with an average of 26.27 meters per second squared and an RMSE value of 5.12 meters per second squared. So it had the highest, which made it the least accurate. The gravity and linear model was a bit better with an average of 25.47, so a little bit less second meter per second squared, and the RMSE value of 5.04 meters per second squared was a little bit less. The gravity and quadratic air resistance model proved to be the best, however, with 24.80, less than the other two, a lot less meters per second squared, and an RMSE value of 4.98 meters per second squared. So it was less than 5, less than the other two, and was the most precise for our data because it accounted for the most. And yeah, that was my this that was my observation on the experiment.